In this video, we're going to be looking at the effects of inhibitors on the values of Km and Vmax for enzyme catalyzed reactions. The following table summarizes the 4 different inhibitors that we just discussed in terms of their binding site, their impact on Km, and their impact of Vmax. The definitions of Km and Vmax, for those of you that need a reminder, are in the bottom of the slide. As you can see, Km is going to show us the concentration of substrate that is needed for an enzyme to attain half of its maximum rate of reaction. And Vmax is this maximum rate of reaction that is present in enzyme catalysis. Now we're going to look at each case in detail. So, when we're talking about an enzymatic reaction, understand that first we should establish what is the general equation for an enzyme catalyzed reaction. So, in these type of reactions, we have an enzyme, as you can see designated by the capital letter E, is going to react with its substrate that we're going to symbolize with a capital S. That is going to turn into the enzyme substrate complex or ES complex. And this ES complex is going to turn into the product, which is designated by the capital P, and we are going to regenerate the enzyme. Remember that enzymes are going to be biocatalysts, so they need to be used in the reaction, but they're not going to be consumed. They are regenerated in order for them to continue catalysis. So, if we have an enzyme that is behaving under Michaelis-Menten kinetics, we can generate a table or a graph in an experiment in which it can illustrate these dynamics. So in such graph, we are going to utilize in the x-axis different concentrations of substrate. And again, this is a generalized table. This is not illustrating specific data. And these increasing amounts of substrates are going to be done in reactions at constant concentration of enzyme. Now, in this reaction, we are going to be looking at the rate of the reaction or velocity, which I'm going to symbolize with the V0. So, if our enzyme is following Michaelis-Menten kinetics, then for some part of our experiment is going to be substrate dependent, and then the enzyme is going to reach its Vmax, which I now will label this Vmax in this orange ink. If we're looking at the Km for this system, remember that this is going to be half Bmax, and this is going to correspond to the substrate concentration that enzyme is going to obtain in order, or is going to interact with to obtain half of Vmax. Okay, so what happens in a situation where now to this reaction we perform a brand new experiment, but we introduce for example, a competitive inhibitor. So in the case of a competitive inhibitor, which I'm going to symbolize by a capital IC, we're going to have the enzymatic reaction, E plus S, forming the ES complex. And that ES complex forming product and enzyme. And remember that when we have a competitive inhibitor, what is occurring to the system is that competitive inhibitor is interacting with the free enzyme And when that occurs, is going to be forming the enzyme competitive inhibitor complex. Now, forming this enzyme inhibitor complex, understand that what it's going to do is going to inactivate a certain portion of the enzyme. Understand that when you are performing an experiment in which now in the vial you have inactive enzyme, the inactive enzyme does not play a role in the value that we will be obtaining for Km, because only Km and Vmax can be measured if we have active enzyme. So that's one of the things that we have to remember when these experiments are performed. Now, I'm going to now draw a curve that, again, this is a hypothetical curve, but this is just the trend that in experiments that are performed with a competitive inhibitor illustrates what are going to be the changes that will be occurring when an enzymatic reaction now contains a competitive inhibitor. So our curve is going to have a line that, as you can see, as we increase the amount of substrate, that line is going to be over time reaching Vmax. So if here I decide to write what would be the value of Km, let's just say that the Vmax here for this line is going to be around the same Vmax that we have for our first line. What we can observe is that this is going to give us a higher concentration of substrate compared to the original one for obtaining half of Vmax. What does that mean? That the Km that we are obtaining in an enzyme catalyzed reaction, that it is in the presence of a competitive inhibitor, which we designate Km apparent. Again, it is because we have some inhibition of part of our enzyme, is going to be increased. So Km appears to be increased. And the reason why our Km appears to be increased is because at lower concentration, there is a better competition of the inhibitor. And the inhibitor is going to be reducing the amount of active enzyme. But as we increase the amount of substrate in sequential reactions, and we have constant inhibitor present in these reactions, as you can see, since the graph tends to reach towards Vmax, that's why overall we see a Vmax that is unchanged. Remember that one of the features of competitive inhibition is that this type of reaction or this type of inhibition can be reversed by the addition of more substrate. Let's look now at what is the situation when we have a non-competitive inhibitor. In this situation, I'm going to write once again my enzyme catalyzed reaction. Enzyme plus substrate forms the enzyme substrate complex. And that enzyme substrate complex turns into product plus enzyme. Now, in this situation, remember that non-competitive inhibitors are going to bind allosterically not only to the enzyme that is free, but also to the enzyme substrate complex, and is going to do that with the same affinity. So if I designate that this non-competitive inhibitor is going to be capital I and C, This type of inhibitor is going to be making two complexes. One in which we have enzyme non-competitive inhibitor, and one in which we have enzyme substrate non-competitive inhibitor complex. If we generate a graph, a general graph for an enzyme catalyzed reaction, under the same conditions that we explained just for a general enzyme catalyzed reaction in the previous notes, we know that we're going to see a curve that will be like this, in which this is our Vmax. And in order to get our Km, that is going to be the concentration of substrate at half of Vmax. And now, if we try to generate a curve for the system in which now we have a non-competitive inhibitor, this curve is going to be looking a little bit different from the one of a competitive inhibitor. This is going to have a curve in which now the Km for the system is going to be unchanged, but the Vmax is going to be decreased. So if I try to illustrate the Km for the system, is going to be the same or unchanged, apparently, from the regular uninhibited reaction. And again, the red line is designated for my non-competitive inhibitor. So I'm going to be writing the trends. So Km in this system is going to be unchanged, while the Vmax is going to be decreased. The reason why we have these observations is because in the case of the Km, understand that because any copies of the enzyme that are still active are going to maintain the same affinity for the substrate, we are still going to be observing the same Km for the reaction. Now, overall, the decrease that it is observed in the Vmax is because you have to remember that Vmax is dependent on the amount of active enzyme that is present, because a non-competitive inhibitor it reduces the amount of active enzyme by a fixed amount at every substrate concentration. That's why overall we observe this decrease. Let's explore now what happens in the case of an uncompetitive inhibitor. When we have an uncompetitive inhibitor, I'm going to rewrite my general enzyme catalyzed reaction. And now we must remember that this uncompetitive inhibitor which I'm going to designate capital IU, is going to specifically going to be binding to the enzyme substrate complex. So when we see the binding of the inhibitor for the system, we're going to make an enzyme substrate uncompetitive inhibitor complex. So I'm going to redraw how would my uncatalyzed enzymatic reaction looks like. Let me label where my Vmax is. Let me label where my Km would be if I consider that this is half of Vmax and this is going to be the concentration of substrate. So that means that this is my Km. So if now I have an enzyme catalyzed reaction in which I'm performing an experiment in the presence of an uncompetitive inhibitor, this is going to have effects on both the Km and the Vmax. And if I write a general curve for it, if I draw what is the new Km of the system, it will be here. At this concentration. And what we see in terms of the effects that the presence of this uncompetitive inhibitor has to the enzymatic reaction is that our Km is going to be decreased and our Vmax is also going to be decreased. So, why do we see these observations? Well, first of all, the one that is, I guess, simpler to understand will be the decrease in Vmax. Remember that in this process, when the enzymatic reaction is inhibited by an uncompetitive inhibitor, we are going to be forming an enzyme substrate uncompetitive inhibitor complex. And when this is formed, the substrate cannot be converted to product, and since it's going to do that at the different amounts of substrate, then overall we see a decrease in Vmax. Now, the decrease that we see in Km, that, remember, in the system where we have an uncompetitive inhibitor, the interesting thing about this is that an uncompetitive inhibitor is going to be binding to our enzyme, because upon binding of the substrate, this enzyme is going to be going into some conformational changes, and it's going to be opening allosteric sites in which now the inhibitors that have been designed will be binding there and making the enzyme substrate complex hold tight to that substrate. Now, the decrease in Km is because when we reduce the concentration of the enzyme substrate complex to make this enzyme substrate in uncompetitive inhibitor complex, what we're in essence affecting is Le Chatelier's principle, in where we shift the equilibrium towards making more enzyme substrate complex to replenish the one that has been in essence been taken away by the interaction with this uncompetitive inhibitor. So that results in having less free enzyme overall in the reaction. The last case that we are going to be looking at is the case of a mixed inhibitor. In a mixed inhibitor, which I'm going to designate as an IM, what is occurring overall, I'm going to rewrite my enzyme catalyzed reaction. What happens in a mixed inhibitor is that now our mixed inhibitor is going to be binding to the free enzyme and to the enzyme substrate complex by different affinities. Okay, so now I'm just going to write a note that the binding is going to have different affinities to the enzyme by itself in the enzyme substrate complex. Because if a mixed inhibitor will have the same affinities for free enzyme and enzyme substrate complex, then that suggests that it is a non-competitive inhibitor, and that is not the case. So when we have a mixed inhibitor, remember that this is going to have effects both in the Km and the Vmax. Okay, in the case of the Km, it depends on its preference. Okay, if it's going to have a higher affinity for the enzyme by itself, or is it going to have a higher affinity to the enzyme substrate complex. So when it comes to Km, if this mixed inhibitor, which is in essence a combo inhibitor, when I mean with combo, is because it's going to have features of competitive inhibitors and it's going to have features of uncompetitive. That's why I consider it a combo. Now, if this mixed inhibitor has a preference or higher affinity for just the enzyme, the free enzyme, then we see an increase in Km, just like we observed in the competitive case. Remember, when we have a competitive inhibitors by themselves bind to the active site. When we are talking about a mixed inhibitor, the feature in which we consider that it is a competitive inhibitor is because it's binding the free enzyme. Mixed inhibitors bind allosterically to the enzyme. They do not bind the active site. The only reason why I say it has features of competitive inhibitors is because it binds the free enzyme. And we observed before that in the case of a competitive inhibitor, we saw an increase in the Km because as more substrate was added, then overall we saw that the reaction reached its Vmax. So the trend of having an increased Km is also present in the mixed inhibitor. Now, if this mixed inhibitor, if it prefers the enzyme substrate complex, it would lower the Km. And again, that's where the feature that it looks like an uncompetitive inhibitor comes from. Remember, in the case of the uncompetitive inhibitor, the reason why we saw the reduce or the decrease in the Km came from the idea that we were now in essence affecting the formation of, or we were affecting the concentration of the enzyme substrate complex. And because we're affecting that concentration by inhibiting it, we are pushing Le Chatelier's principle, meaning that we are combining more enzyme and substrate in order to reestablish the equilibrium and form that enzyme substrate complex. So when we look at the Km, that gives us the ability to see that there's less free enzyme in the system. Now, when it comes to what are the effects on Vmax, in Vmax, the effects are that overall it is decreased. Now, the reason why Vmax overall is decreased is because either way, this mix inhibitor is going to be reducing the concentration of enzyme and enzyme substrate complex. So remember that there's a dependence of Vmax on the ability to have active enzyme, and now that we are going to be inhibiting it, that is going to have an overall effect of reducing the Vmax.